All right, so let's get started here. Hello, it's a pleasure to introduce our Vamos speaker today, Dave Weiss of Penn State University. As many of you know, Dave is a pioneer in a number of areas in ultra-cooled atoms. He made early significant contributions to the field of laser-cooled atoms and optical lattices and novel methods for high-fidelity ground state cooling in these systems. And he was an early proponent of the idea of combining this kind of laser cooling with high filling arrays to reach low entropy systems as an alternative to evaporative cooling. And this is a concept which actually echoes today in a lot of different people's work in lattices and tweezer systems. In particular, he's been a leader in using these techniques to make strides towards a neutral atom quantum computer. In parallel, Dave has also made seminal contributions to non-equilibrium dynamics of cold gases, and in particular, studying the conditions under which these systems thermalize and the mechanisms that govern this process. This has been a rich field about which I think I'll say no more since this is the topic of Dave's talk today. As a reminder, you can ask questions in the Q&A for the Zoom and in the chat for the YouTube Live. So with that, thank you for being here, Dave, and take it away.
Thank you, Adam. I'm happy to be here. I'm a pretty regular Vamos watcher. It seems like it's hard to know how we got along without it, really. It took a pandemic to do it. So I just, as a technical note, if you're watching me on, I think on Zoom, you can just put me in this box, and I've cleared that box for you up in the upper right-hand corner. So it'll keep you, it'll hopefully improve your viewing experience. So I'll be talking about extremely out of equilibrium 1D gases. The team in my lab that's been working on this is Josh Wilson, Neil Malvania, and Yuan Li, with theory collaborations with Yicheng Zhang and Marcos Regal at Penn State, and then Jerome Dubai at University of Lorraine. The rest of my group works on experiments to make a neutral atom quantum computer, as Adam pointed out, and then also a search for the electron EDM, work supported by the ARO and the NSF. This is a relatively recent picture of my group. I never see them in person, but this is what they look like now. They're the people I just mentioned. So the idea here and the experiments I'll be talking about is that you have if you have a many-body quantum system, the dynamics are difficult to calculate, and it's, because there's all sorts of correlations. It's an inherently complicated, rich dynamical system. There have been a number of specific kind of theories that have been able to address them, but in very limited ranges. But there's a new theory called Generalized Hydrodynamics, which I'll talk about as we go along, which allows you to do calculations in systems that are not strictly interval, but nearly interval systems. And that new theory has not really been tested in experiments to see if it applies, and that's what I'm going to be talking about today. Eventually I'll get to that. So the outline is I'll start off explaining what fermionization is in a 1D gas, and then I'll talk about the momentum distributions in 1D gas. I'll define what rapidities are in the 1D gas, and I'll show you what dynamical fermionization is. I'll talk about how we do momentum measurements in our lab, and then how we've observed dynamical fermionization, which is a measurement of rapidities, something which hadn't previously been measured before, an important part of these nearly interval systems. Then I'll explain Bose Fermi oscillations, and then the theory of generalized dynamics and how we test it in the lab. So going back quite a way, if you have a 1D Bose gas with infinite point contact interactions, Harmonic interactions, Girardot showed that there is a formal equivalence between the many-body wave function for the bosons and the many-body wave function of the fermions, where they're the same except for this absolute value sign, and that's been called fermionization. He called it fermionization. It's been called that way since there. And it's basically because with this large repulsion, two single particle wave functions can't overlap, so it functions a little bit like a Pauli exclusion principle. And I sometimes show that with a cartoon illustrating these correlations. You have a bunch of bosons together, the probability of two of them being in the same place is very low. And it's not to say that there's a particle here, a particle here, a particle here. This is more of a cartoon to illustrate what the correlations are. The point is that if you measure a particle here, you're not going to measure another particle in the same place, right? Because this wave function is not just a bunch of separate atoms, it's a highly correlated many-body wave function that just has this property of having no two in the same place at the same time. Another way to understand how that comes about is to consider just the two-particle wave functions, the relative wave function of two particles, where if you had no interactions and you had bosons, the two-particle wave function has to look like this, because it has to be a symmetric wave function. So if the particles have a relative momentum, which is determined by the period of that sine wave, this is what the wave function looks like. Whereas if you have fermions, same thing, but it has to be an anti-symmetric wave function. If you have infinite repulsive delta function interactions, like the Tongue-Shiro gas, then you still need to maintain the same symmetry, but the particles can't overlap at the origin. So the wave function has to look like this. Now, if you look at the Fermi gas, or two fermions together, if you take the absolute values, like multiplying by the signum function, this is what Girardot's mapping is. And you see that the Girardot's mapping is the Tongue-Shiro gas, right? So that's how the fermions and the strongly interacting bosons are alike. But really what you're comparing is, if you want to compare to fermions, it's the Tongue-Shiro gas, which is actually this, and the fermions. So if you look at any property which is local, anything which depends upon the point contact of particles in the same place, and that includes things like energies and spatial distributions, local pair correlations, they're the same for the Tongue-Shiro gas and the Fermi gas. But if you look at non-local properties, like momentum, which is to say, if you know the wave function over here, what's the wave function over here? It's different for the bosons and the fermions. So this fermionization that Girardot showed is within this absolute value sign. It's not a fermionization of all properties. Lieb-Liniger, just a few years after Girardot, solved an equation interacting many-body Hamiltonian with not an infinite point contact interaction, but a variable energy point contact interaction. So it's simple Hamiltonian, just a kinetic energy term, this interaction term. And they showed that by doing beta ansatz, you can get solutions which are parameterized by this dimensionless coupling parameter gamma, which I'll refer to as we go along. This is an integrable model because it lends itself to a beta ansatz solution. And what that means is that there's extra constants of motions, and those extra constants of motions are called the rapidities. Because it's integrable, because there's all the extra constants of motion, the wave functions and all the local properties are exactly calculable. I'd note that if you put this Lieb-Liniger gas into an axial trap, that lifts the integrability, but really pretty slightly. So that's a weak lifting of integrability. Many of the features of integrability, like these nearly conserved quantities, remain, and that's part of what we'll be explaining with GHD. The next step in the history is a long gap to 1998, where Maxime Alshani showed that with real atoms in waveguides, there's a mapping to the Lieb-Liniger Hamiltonian. So you can actually make things that are a pretty good approximation of this Hamiltonian by trapping atoms in the ground state of a 1D of a tube. So to understand the different Lieb-Liniger regimes, it's all you just have to do is look at the dimensionless coupling parameter. When the dimensionless coupling parameter is large and gamma is very large, that's like this being the G1D being infinite. That means that you have a Tongue-Shiro gas. So with regard to the particles' interaction with each other, the kinetic energy associated with them avoiding each other is the dominant thing. Basically, it's too costly to have the particles overlapping at all and having a mean field interaction energy, so it doesn't happen. And then in the opposite regime, where gamma is very small, the mean field energy dominates. It's a little bit more like a Bose-Einstein condensate, because that's not such a big energy cost compared to the energy cost of having the particles avoid each other. And in general, gamma can be anything. And then in this cartoon picture, you'll see there's some intermediate probability of the particles overlapping. So in the Lieb-Liniger model, it's been realized in the lab in many places, and many of the properties that you could possibly measure have been measured in a large number of labs around the world. I'd say that the current experimental and theoretical frontier are not the equilibrium properties, but the out of equilibrium properties. And less the properties that are fermionized in equilibrium and more the non-local properties that, and it turns out that these things are much harder to calculate than in general than the local properties. And particularly the theory in the two extreme limits is a lot simpler than the theory anywhere in between. Maybe not surprising. So I'm not going to show too much in the way of data, all these experiments that are happening. I'll just show you one because I think it gets to the essence of it. An experiment we did a while ago using photo association to see what the local pair correlation function is, the probability of finding two particles at one place, and as a function of the gamma over a bundle of tubes. And you see that as you vary the gamma, the probability of the particles overlapping decreases. So this G2 would go to 1 with very weak coupling, just like a BC, and then G2 would go to 0 when gamma is very high. That's like a non-interacting Fermi gas. That's sort of like the Pauli exclusion due to this strong coupling. And then you can see everything in between. And this is an exact theory, so that there's no free parameters in that. It just matches what you see in the lab. Just to say that in equilibrium, we can clearly make these gases. Okay, so now I'm going to turn to the rapidities because that's to a large degree the subject of the rest of the talk. And rapidities have two different definitions, usually in that are used commonly. And one is that they're the set of conserved quantities in an integrable system, right? So because it's integrable, things can't thermalize. There's a constraint associated with all these conserved quantities, and that's one sense. And the other definition that you can have is that it's the momentum distribution of the quasi-particles that arise in this interacting system. Now, what do I mean by that specifically? It's to say that I've given a cartoon picture of single particle wave functions in space, but I can give another cartoon picture of quasi-particle wave functions in momentum space, or in the momentum of the quasi-particle space, which is the rapidities. So whatever these wave functions are for the particles interacting, if it's an integrable system, you can look at that as a bunch of quasi-particles with some distribution of quasi-particle momentum. So there's not a one-to-one correspondence here. These quasi-particles are generated from this the atoms in the gas in ways that are relatively complicated depending upon what gamma is. But the point is that these quantities over here, the rapidity distribution that you have, are the conserved quantities in the Lieb-Liniger gas. Now, in a homogeneous system, these two definitions are exactly the same, right? Because you can sort of see why that is. The momentum distribution of the quasi-particles, if you're just moving in free space, don't change. There's nothing making them change. So they are just conserved. So they are the set of conserved quantities. But if you put the particles in a trap, then they're not the same, because the quasi-particle momenta, if you're moving in a trap, if something is happening in a trap, are not, they can be changed because of the force exerted by the trap. What we're going to do is we're going to use the second definition, because that turns out to be much more useful when you are in a trap and when you take the systems out of equilibrium. And that's the core thing that generalized hydrodynamics uses. All right, so this is our definition of rapidities, the momentum of the quasi-particles that emerge in the system. So just to practice on the simplest possible case, suppose you have a 1D harmonic trap, 0 temperature. If you had non-interacting fermions in that trap, there would be a momentum distribution, which, if it was a flat trap, would just be a flat distribution of occupation. But in the harmonic trap, there's going to be some Thomas Fermi kind of shape. If you look at a Tonk-Trudeau gas, the momentum distribution is not the same. It's much more bosonic. It's heavily peaked in the center with these wide tails associated with the particles avoiding each other. Okay, so the momentum distribution is not the same. That's not the part that's fermionized. Now, if you look at the distribution of rapidities for the non-interacting Fermi gas, it's the same as the momentum distribution, because the particles are just the same as the quasi-particles, right? Those are also would be the conserved quantities in free space, And, that's not conserved necessarily in this harmonic trap, but they are the rapidities by the second definition. And the rapidities of the atomic shared O gas are just like the rapidities of the non-interacting Fermi gas, right? That part of the set of conserved quantities are the same as a set of conserved quantities here. Now, from this trap, if we just turned it off, then first, the act of turning off the trap doesn't change either the momentum distributions or the rapidity distributions. And it's just that from the point at which you turn off the trap, then the rapidities would actually be the conserved quantities, right? Because that would be transitioning to a homogeneous system. Okay, so now I'm going to get to what is really the an important central thing to understand to get at the rest of what I'm going to be showing you, which is that if you have particles that are initially trapped and you let them expand in 1D, so you keep them in 1D as they expand, then eventually the density of the particles gets very low. And all the energies associated with the particles overlapping, either the mean field energy or all this energy associated with them avoiding each other, become very small. And as you do that, the particles, the quasi-particles that define them start to become just the bare particles. There's not a lot of interaction energy to make quasi-particles out of the bare particles. And what that means is that their asymptotic momentum distribution is their initial rapidity distribution. And because their initial rapidity distribution is exactly the same as their final rapidity distribution. It's a conserved quantity. And eventually that momentum distribution the rapidity distribution, which doesn't change, the momentum distribution becomes what the rapidity distribution is as these things expand. And that has been understood before, but that is really the crux of how we're able to measure the rapidities, as I'll be talking about. So the first example of this, the original concept of an experiment for doing this came from Marcos Rigol when he was a graduate student, which is that if you have in the gas, in a trap, a harmonic trap, a atomic shared O gas, and you compare that to the momentum distribution of a Fermi gas, and you let it expand, as the certainly if you let the Fermi gas expand, nothing changes because there's no forces on it, there's no interactions. It'll just be the same. But if you look at the momentum of the bosons, they eventually approach exactly the momentum of the fermions. Right. So that is dynamical fermionization, is that this other property of the interacting Bose gas eventually becomes the same because the thing that was the same at the beginning was the rapidity distributions. Right, so that's dynamical fermionization. So I don't know if there are any questions at this point. Now would be an okay time to answer some of them before I.
Yeah, we have a couple questions here.
Okay.
So the first question is from Bill Phillips.
I was hoping.
And he asks, can you comment on I cannot say that word. Okay.
Fermionization.
Yeah, in higher than one dimension. Hardcore seems to imply the same exclusion, but I don't hear about it in 2D or 3D.
Well, I mean, to the extent that the fermionization, this absolute mapping requires the use of the beta ansatz, it doesn't really work past 1D. So it is a 1D effect. There, you can define gamma in higher dimensions. You can define this dimensionless coupling strength. That's not specific to 1D, but yeah, it's not. You're not going to get. As far as I know, in higher dimensions, you don't ever have, say, bosons looking just like fermions, mapping in this formal way.
Got it. The next question is from John Kunjaman, and he asks, for trapped systems, can you view the rapidities as quadratures of simple harmonic oscillator motion instead of as momenta?
No, I mean, it's the momentum of the of this emerging quasi-particles. The problem is that in order, the rapidities inherently depend upon the interactions among the particles, right? So you wouldn't have anything like the rapidities in a, once there's these strong interactions in the cell, or any sort of intermediate, interactions in any of these regions. So the rapidities don't look like just things associated with the trap, right? The rapidities overwhelmingly are dominated, except for in sort of some trivial instances, they're dominated by the interactions among the particles. Yeah, so you're not going to simplify the concept of the rapidities by just with reference to any single particle thing in the trap.
Got it. Okay. Actually, I have a question, which is the mapping of the rapidity to the momentum temperature independent? And I'm sort of asking that from the perspective that I might expect that non-adiabatic effects might occur, which wouldn't preserve the mapping.
No, it's totally, it doesn't depend on gamma, it doesn't depend on temperature, it doesn't depend on anything, because as long as you go into flat space, then as long as you have a system which is close enough to integrable, then those are the conserved quantities. And by the time the thing sets out, then the quasi-particles look like the real particles, and you're going to see the rapidities. So it's robust to anything as long as it stays close enough to integrable.
Okay. I see. Okay. Okay, and then we have another question from Bill Phillips. He asks, expansion, as you say, leads to small interaction energy, but it also leads to large gamma. Could you comment, ?
Yeah, so the, first, once you're expanding, it's not an equilibrium system, right? So you can't expect to get what you might expect at a high gamma in equilibrium. But, there's sort of something which is maybe underneath that question, which made me uncomfortable for a while. Maybe it's making Bill uncomfortable, is that you have this the system which, in the limit of large gamma, fermionizes for spatial distributions. And now after this long time, you say, oh, now it's fermionized for momentum. But they're bosons. How can they both be fermionic, both in terms of their momentum distribution and their spatial distribution? And Marcos has looked at the answer to this, and it turns out that if you look at all the other properties associated with this many-body wave function, they're all totally different, right? The correlations, the non-local properties, not anything other than the momentum, look totally different as you do this expansion. It's not an equilibrium situation. It just turns out that these two things, the spatial distribution and the momentum distribution, which again, just ignores all the other correlations involved, are just like the fermions.
Okay. And then maybe one last question before we move on. So this is, from Dan Semperkern. So he asks, does the mapping onto fermions depend on the particles being indistinguishable? So for example, would the experiments, okay. Okay.
Yeah, I mean, I think you end up with a lot of sort of trivial stuff if the particles aren't indistinguishable.
I see. So it's not just strongly interacting.
Right, right.
Got it. Okay. All right, why don't we keep going?
Okay. So I'm now going to switch to how we do this in the experiment. It's many people may be familiar with this apparatus. I'll just walk you through the essential points. We have very large blue detuned optical lattice beams shown over here. And they give you a bundle of tubes where, the tubes over here are separated by half a wavelength, wavelengths like 770 nanometers. And then since it's blue detuned, the atoms are nearly free to move along the trap. So we trap them axially using this cross dipole trap, which allows us to then have them trapped independently in the axial direction from in the transverse direction. Because the lattice beams are very large, the 1D confinement is nearly the same at all the tubes that we occupy. And, they're actually, we're confined really reasonably much to the center of these this cross dipole trap too. So the actual frequencies are about the same also. Well, there might be as large as a 13% variation of the axial oscillation frequency across occupied tubes from sort of the center tube to the least one that's occupied. in each tube, we have somewhere between, I mean, in the experiments I'm talking about, between 0 and 25 atoms per tube, or between 0 and 140 atoms per tube. And there's on the order of 100,000 atoms. These are 1D systems because all the energies, we start off with the Bose-Einstein kind of set, and all the energies are small enough that we never have enough information to have a transverse excitation within a tube. And we also have the lattice kept at a deep enough level, this is 40 recoils, that the tunneling from tube to tube is negligible on the time scale of the experiment. So the way the dynamical fermionization measurement goes, and again, that will become our generic rapidity measurement, is we first start off with the Bose-Einstein kind of set and turn on as adiabatically as we can this lattice around the atoms. And then we turn off the axial trap, which allows the atoms to evolve in the tube, still staying in one dimension. Right, and we actually don't completely turn it off. We keep a little bit of it on so that the potential that it's in that axial direction is pretty flat over a reasonable distance. And then we let the atoms evolve for some time in that 1D tube as they're expanding, and that's a variable time, we'll call it T evolution. And then at some T evolution time, we then measure the momentum distribution. And I'll tell you on the next slide how we measure the momentum distribution. And then we compare it to theory. Okay, so the way we measure the momentum distribution, again, which is measured at some point after it's expanded for some amount of time in the 1D trap, this is an edge-on view of a few lattice sites, is we rapidly turn them off. So you rapidly turn them off, these initially tightly confined atoms are now spread out, and all the interaction energies in one dimension become much smaller. And they become very fast because we let them just fly apart. You know, they're trying to get them flying apart as fast as possible. Like the interaction energies decrease by a factor of about 20 before they run into the next tube. And essentially, it makes the 1D momentum distribution stop evolving very, very close. And we can check that out experimentally, that we're turning these things off. And under most circumstances, there's no change to the axial distribution depending upon how, we turn it off fast enough that there's no change. If you turn it off slower, you can see a change. So what that looks like is here, where the one dimension is up and down on the screen. So we have the atoms trapped in this direction. We do the sudden turn off. They very rapidly, very quickly expand to the side by a lot. Right, this is after some fixed time of flight. And just to keep the scale, our initial transverse confinement is only about 20 microns there. Okay, so they've really expanded a lot transversely. They don't expand that much in the axial direction, but that's what we're trying to do. We're measuring the distribution by integrating along this direction. We measure the distribution in this direction. And this is actually what happens first if you just turn off everything. So there's no evolution time in 1D. That's what the distribution looks like axially. And then after 15 milliseconds, where it's the same, the time of the actual shutoff is exactly the same. It's just now there's been 15 milliseconds where it's expanding in 1D. This is what the distribution looks like, right? So clearly something is changing the momentum distribution, which we're going to get the momentum distribution from a time of flight here. And this is what we see. Okay, so the initial distributions is that first picture over here is the purple one. You see it's peaked up like this bosonic distribution I talked about. And then gradually over this time, it asymptotes to this thing, which is much more hump-like, which is the fermionic distribution. So it asymptotes to the fermionic distribution. And then we see, it's almost asymptoted by 12 milliseconds, 15, you can sort of see these are barely changing, but we can't go longer than that because that's sort of the spatial limit of our flat potential. Okay, so that is the observation of dynamical fermionization, but is it really that? Well, we also do the theoretical calculations where this is in the Tangström limit. So this is not this is a situation where the experiment was done with an average gamma of about 8. So it's high, it's not infinite. And we look at this momentum distribution in the theoretically in the infinite coupling limit. And this is a detail about how that's done. It's you put the free space onto an artificial, very, very fine lattice, particles can't be in the same place, and then you can numerically calculate wave functions as they evolve. We include everything that's happening in the experiment in the calculation, including the sum over all the tubes, the instrumental resolution, and also just the, the details of the timing of turning on or off these potentials. So you see it looks qualitatively similar. This is the direct comparison at each of those times. Again, there's not free parameters on it. You see by the time you get to 15 milliseconds, they are pretty overlapped, right? That contains both the theory and the experiment for the distributions. So I'd say, there's a little bit of a disagreement over here. I think the larger part of that is that the gamma is not infinite, and maybe probably the temperature is close to infinite, but it may not be exactly zero. And that makes a little bit more of a difference to the initial momentum distribution. But that energy is irrelevant by the time you do this expansion. So anyway, it works pretty well. So the question is it really the measurement of the dynamical fermionization? The answer is yes, and that's because I can show you that with these 4 different curves. One is the experiment, which is in red, and then in black, that's the theory with no free parameters. So the theory of the actual experiment that we do, no free parameters, and that's the thing which is really pretty good agreement across those. So the experiment is certainly well described by this Th theory, at late in the expansion anyway. And then in the mustard colored, that's the momentum distribution of the TG gas, which you can get from the theory. And you can see, since that is very close to what we're actually seeing for these 2 things, that means that the finite size effects, the resolution effects, none of those are significant. What we're actually looking at in the experiment is the asymptotic momentum distribution, or anyway, the momentum distribution of what a TG gas would do. And then the final thing is, what would you get if you looked at the momentum distribution of a non-interacting Fermi gas, theoretically? And you see it's pretty good. There's a little bit of variation over there, which would eventually go away if we could expand for a longer period of time. But to the extent that all this stuff agrees with itself pretty well, it just says that the evolution time is long enough that we have actually asymptoted to the shape. I mean, if you look at the theory, in a long enough time, the theoretical distributions would have completely overlapped the non-interacting Fermi gas, and they almost do in this thing. Okay, so that's why I say we measure the distribution of rapidities. And so I'm going to, I'll talk a little bit more about Bosonic-Fermionic oscillation before I get on to what we do with the GHD. So it was also theoretically observed that if you quench from one axial trap, say this in this case a deep trap, to something which is much shallower, then what was seen experimentally first by Minguzzi and Gengart is that you start off with a bosonic momentum distribution. And then after a short time, that bosonic momentum distribution becomes a fermionic distribution. And you can say that kind of makes sense straight off, because that's a little bit like dynamical fermionization in this early time where you go from a deep trap to a shallow trap. It's not quite zero, but it's much shallower. You get this fermionized distribution. And the thing which is a little bit more surprising and notable is that at the point where it turns around, the momentum distribution, which is now much shallower because you've taken away a lot of the energy going up this shallow trap, ends up also being a bosonic distribution. Okay, so momentum distribution oscillates from bosonic to fermionic and back every half cycle as this gas breathes. So we did those experiments measuring momentum distributions. The experiment are the blue curves, and the theory are the red curves. This is a theory using the Th gas limit. So you see, they're not exactly the same. They're qualitatively very similar, but clearly the theory doesn't quite apply, because here we start off with a gamma of 8, and the average gamma becomes at the highest point of compression more like 2. It's really not the Th limit. But it's interesting, if you rescale, if you sort of fix the phase of these things and then rescale the shape, rescale the height and width of the function so you can compare the shape, you still see in the experiment these things which go from bosonic to fermionic in shape. So bosonic, fermionic, as it just repeats itself as it oscillates. Okay, so here that's the dynamics of the momentum, and there are no existing methods, including anything I talk about now, that can actually give you these momentum distributions dynamically. Right. So the thing which is most notable about this is that the qualitative behavior, even in really intermediate coupling, is similar, but again, not exactly the same. There's features in the theoretical distribution which are not really shown don't really show up in the experiment. Okay, qualitatively it shows what you'd expect. Here, that was quenching to a higher trap depth. This is quenching to a lower trap depth, where you stay to a greater degree in the higher gamma limit. And you see the same thing. It's bosonic-fermionic, bosonic-fermionic. Still some features in the theory which don't show up in the experiment. But, so certainly for these features, the TG theory works better, but we really need something which is better. And that is generalized hydrodynamics. Maybe I'll do just this slide first, and then I'll take a break to answer any questions about that before I show you the actual results. So generalized hydrodynamics is it's a hydrodynamic theory, as the name suggests. It's but it contains in it these rapidities. It's a hydrodynamics of the rapidities, keeping note of the fact that they are locally conserved quantities, even though they're not globally conserved when you're moving in a trap. So it's that just looks like a hydrodynamic equation. The thing which is their density is actually a Fermi occupation ratio. It's like a normalized density, and it's a function of the position and the rapidities as well as time, right? So it's a coupled equations that keep track of the density in space and the entire rapidity distribution in space and as it evolves. And the tricky thing, which I'm not showing, is a little bit involved to see it, although I can refer you to these papers or to our preprint on this, is in this effective velocity, which is chosen in this in the numerical calculations so that you locally satisfy the generalized Gibbs ensemble, which is to say the gas is locally thermalized to within the constraints given by the particular distribution of rapidities at each spatial point. So you let the things evolving, making sure this local GG is satisfied, and then you get your couple equations. That's your generalized hydrodynamics. So the assumptions that underlie this are, one is that you can describe the gas with a continuum approximation, because you're just talking about cells and you're saying everything is smooth. And you have to be sure that the gas is actually equilibrated to the local GG at every point, right? Because if it wasn't, then this whole thing would fail. So GHD has been previously demonstrated in one experiment. So the first to really apply the theory to experiment. I just say it was in the reasonably high temperature, high compared to the quantum degeneracy temperature. I meant high, but comparable to quantum degeneracy temperature in the weak coupling limit. So where it's a little more like a BC, and with a fairly modest quench. You start off with two groups of atoms and just let them come together over there. See, it agrees incredibly well. And what I'll be talking about is we're testing GHD near zero temperature in the regions where there are strong correlations, strong and intermediate coupling in the gas, and we're doing very large quenches. So before I show you that, I can take a little break, answer questions.
Sounds good. Okay, so we have two questions here, possibly a third one coming in. So the first one is from Bill Phillips, and he says, it seems that the blue tubes, so this is like earlier in the talk when you were showing the tubes, alone would create a little bit of an anti-trap as a pseudo-potential. Right. Is that right, and does it matter?
It's right, and it does matter. So what we do is we leave a little bit of the red light on to cancel it out. And that's why we can't do because of the weights of those two different beams aren't matched, that we can just sort of come very close to matching them over some finite range. But yeah, I mean, you can't ignore the anti-trap from the blue lattice, even though it's a half a micron lattice, so it's a very modest trap, but it's enough to make a difference. So you do have to counter it, which we do.
Okay. Monica Schleier-Smith asks, is there a particular fit parameter that quantifies how bosonic or fermionic the momentum distribution is?
Yeah, that's a very subtle, deep question. Not really, right? So, and one of the problems is that you could imagine if you just had a single tube, you can imagine, say, comparing the distribution to what the full bosonic distribution look like, or let's say the initial zero time thing looks like, and comparing that to, say, the dynamically fermionized distribution, and you can see how close they are to each other. And we've done that, and it actually works pretty well. The fits are good when it's bosonic-like, and if it's bosonic-like, and vice versa. The problem is that what we do is an average over tubes, and that kind of complicates it. So we found that even though we can get something which looked okay in comparison Bose fermion, it's just it's more like you look at it, you can sort of tell that these things are alike. And what we're doing is we're actually comparing it to the actual theory at those points, right? So the comparison was not to bosonic or fermionic. The comparison is what does the time short of theory look at those points? Look like at those points.
Okay. And then and she asks, how can you confirm or check the equilibration to the local generalized Gibbs ensemble experimentally?
Okay, so that's what I'll be showing you now. It's basically showing that what we're trying to do is we're trying to push that limit as much as we can, and then so the test that it's okay is really the test of whether GHD works, right? So that's, in a sense, that's what we're doing now. In testing whether GHD works, we are testing whether these two assumptions are right. So that's the way to do it. Otherwise it's you'd be hard. It's a little harder to know.
Right. Okay, and then one more question, then we'll keep going. This one's also from Bill Phillips. He asks, this might be actually a record for Bill, so I think that's important. So remembering that in 3D, expansion of a Bose gas and a Fermi gas are only subtly different, and that the Kasten-Dumm expansion of a Bose gas goes to a Thomas Fermi shape in momentum, can you assure us that the agreement is not accidental?
That the agreement between
I think he means between the Tonks Giraudoux theory and the experiment. And perhaps Bill can write us an email if
I would just say that if I go back to here, this shape is pretty different from this shape, right? So this is what you get if it's just bosonic, and this is what you get if you're over here, or if you look at them all together. That's not just a change in, that's a change in shape. The energy actually doesn't significantly change over that range. That's conserved. So the rapidities are conserved, the energy is conserved. So yeah, this distribution is pretty different from that. It's not coincidental. I just, look, it's really the same, right?
Yeah.
Okay. So yeah, I don't know if that satisfies Bill. Maybe he probably has something else.
Yeah, maybe he'll follow up.
Okay.
But maybe we can keep going then, Dave. Thanks.
Yeah. So okay. So so this is the first thing you did. We started off with gamma equals. It was actually the second thing we did. The first thing I'm going to show you. We started off with gamma equals a 1.3 gas, and we do rapidity measurements, not momentum measurements, at every point in time. Right, so there's no T evolution because it's always a rapidity measurement. And each of these rapidity measurements is at least as good as the one we have with the Tonks-Giraudoux gas when we were doing that in the other limit, because the density is higher, and how long you're so you can effectively expand for longer in the 1D tubes while you still have a flat potential. Right, so given that we validated rapidity measurements for the Tonks-Giraudoux gas, or the thing which is gamma equals 8, everything else we're doing over here is a better rapidity measurement than that. Okay, so here is a case, there's about 60 atoms per tube on average. You see that there's the reddish colors are the experiment, the blue is the theory. It agrees pretty well. And the other thing, which I don't know, you can't tell looking at it over here, but if I scale them, if I take, say, all the experimental points and then rescale them so I can compare the shapes. This is the things, selected things from the first cycle. This is selected from the second cycle, to say that everything is self-similar. Right, the rapidity shape, even as the rapidities themselves are changing, the distribution stays the same shape. Okay, so first thing, generalized hydrodynamics quantitatively reproduces what the experimental rapidity distributions are in terms of shape, size, everything. Okay, so then we start off with a higher gamma. So this is a 9.3, and we do a 100 times quench in the depth of the trap. So we go from a shallow trap to something which is 100 times deeper. So this is the rapidity distribution as a function of time. It starts off, it's narrow, and as time goes on, you see it evolves, gets wider, gets narrower again, repeats. This is the first cycle, this is the second cycle. So that's the experiment, and this is the experiment with the theory. On top of it, the blue is the theory. So you see, this is in a case where the agreement is pretty good across the board. Here we have an average of 11 atoms per tube, which means that we're testing this continuum approximation pretty seriously. There aren't that, with 11 atoms, you might think that, maybe this continuum approximation wasn't good, but it turns out it's not a problem for GHD. And here, if you look at the rescale distributions over the first cycle, it is approximately the same shape every time. But then by the time you get in the second cycle, you see the actual, obviously the size and the light changes, but the actual shapes are starting to change too as you go along. All right, I'll be talking about these shapes and everything a little bit more as we continue. But first, just, I think to most people, it's surprising that so few atoms can still be surprised by a continuum approximation. We see it from the experiment. And we thought about what can we test theoretically to see if that makes sense. So Yicheng and Jerome did calculations on comparing GHD in the Tanshiro gas limit to an actual theory in the Tanshiro gas limit, because that's the only theory that we can actually solve exactly. The GHD's approximation, this is an exact theory. And you see this is for either 5, 10, I think I have the things labeled wrong, but because it's 20, 10, 5. For those different very small numbers of atoms, the GHD overlaps essentially perfectly with the exact theory, except for the exact theory has these extra wiggles, Friedel oscillations associated with the quantization of the thing. It's not there in the theory, in the GHD, because it's a continuous approximation. But certainly, if you don't have those wiggles to worry about, it's exactly the same. So, it's maybe not surprising that it works well even for these small number of atoms. Right, we can check it over there. At lower gamma, we can only check with the experiment. So this is what the evolution of the theory looks like, and it's just a little bit of a sample. And so that what we're plotting up here is the rapidity on one axis and the spatial distribution on the other axis. So it's like a phase space and rapidity curve. I'd note that the area of these things would be conserved, but in the first column, this is the first cycle, second cycle, third cycle, fourth cycle. First column is a different scale for both of those things than all the later ones. These are near the point of maximum compression, just a point at the point of maximum compression, and then near the point of maximum compression. And what we're plotting up is the Fermi occupation ratio, which, since we're starting off at 0, is either 1 or 0, like 1 in the center, and then where it's white, it's just 0. So you see that the thing evolves in a way which is not really trivial. It evolves and it starts getting this curvature and the like. And if you look closely, say at a given spatial position and what the distribution of rapidities at that spatial position is, you see even in the first cycle, at the first compression, there's a discontinuity that Fermi see. It's like there's a group of atoms, a range of rapidities, and then a gap, and then another range of rapidities. And by the time you get to the fourth cycle, you see 3 different ranges of rapidities over there. And that sort of thing can't really be accommodated. That physics can't be accommodated by any sort of classical description that you might want to have to try to approximate what's going on over here. As far as we know, the only way to do it to this point is with GHD. So you can also look at what happens in space. And this is our initial spatial distribution where it gets really tightly compressed. Then it becomes big again. That was the first cycle. And then over here, this is going to come out for the collapse on the second cycle. It gets really high, and then it comes down over here. I'm stopping over there. I would say, you know, this is why I'm calling it extreme, right? This like counts as extreme excitement over there because we're changing the size of this gas from what is an initial length of 17 microns. It goes down to a half a micron, right? It's a really dramatic change in what's happening over here, but the theory follows what's going on pretty well. Here I'm showing you what's happening on average. This is what's happening in the central tube. If you look at sort of what the spatial distributions look like at the center, so if I just kind of stop what's happening in the center, you see that the central tube and the average don't look that different from each other. They're sort of comparable size, but there are, you know, features in the shape, which, you know, you're also getting that from the kind of curves that I was showing you, the plots I was showing you on the previous slide. Okay, so I've showed you now the experimental rapidity distributions and compared to the theory, and also just the theoretical spatial distributions. But there's something else that we can extract from this, which is based upon the energy from the rapidity distribution. So I just want to go back a little bit to what the data looks like. So this is an example of a measurement of rapidity at one point. It's at a point sort of near the top of the compression, but not at the top of the compression. And then we integrate over this direction to get a distribution. And then to determine the energy, we just integrate up the energy from the center. So, you know, weighting it by basically the distance squared, because, you know, this distance in this direction is proportional to the momentum, or it's proportional to momentum, and it's therefore also proportional to the rapidity, because we've already expanded it to get the momentums to become the rapidities. And then we integrate it up, and you see that you see these points. These are just from different curves of that compression. You see you integrate up the energy, and then at some point you hit the tail, and there's no more integration. And, you know, really just our ability to tell what the energy is a question of how well we can treat the backgrounds. You see, because of these very flat points over here, we're doing a pretty good job of getting a reliable energy measurement from these curves, right? That's something which is technically a little bit tricky to do, but I'd say we've done it successfully. We don't usually average over this point, because at this point, you have just a little bit of noise, but it's really magnified by this z-squared factor. Okay, so from where this thing asymptotes, that tells us what the energy is. So this is showing you now what the evolution of the energy of the system is for this 100 times quench as a function of time over the first two cycles. And the red curves are the data. The blue points, which are, you know, the red points are the data, and the blue points just behind them, in most cases, is the GHD theory. Using we have some fluctuation in the number of atoms. We use the actual measured number of atoms for the theory. You see it agrees. And just as a guide to the eye, we take this sort of fixed average number and get the dashed line. So you see, you know, for the agreement of how the energy evolves, it's really remarkably good across this whole range through the first cycle, second cycle. Okay, so this is what I just showed you a moment ago. And we can do the same thing now with momentum distributions to extract the energy from the momentum distribution, and that's just the kinetic energy, right? This is the total energy from the rapidity distributions. From the momentum distribution, that only has the kinetic energy of the gas. The interaction is taken away right at the beginning. And you see this, and here, we don't have a theory for the momentum distributions, but we can, by looking at what is the gamma at every cell, we can determine how the energy is split between kinetic and interaction at each point, and therefore infer what the total kinetic energy is from the GHD theory. Okay, so we don't have access to the theoretical momentum distributions, but we do have the access to the theoretical kinetic energy at every point. And you see it agrees very well, except for over here, and that's sort of the point at which our experiment runs into a problem, because the interaction energies are so high at that point, the density is so high that we can't quite turn it off fast enough, and we convert a little bit of kinetic energy into a little bit of interaction energy into kinetic energy at that point. But everywhere else it agrees remarkably well. So if you take the difference between these two things, that's the interaction energy. And really you just want to compare the blue to the red. It agrees pretty much everywhere except for at the peak where the kinetic energy is, so the theory is the red, the experiments, the theory is the blue, the experiment's the red, and it's showing the interaction energy. Just to be clear, if we didn't have to worry about number fluctuations and these things were synced, the theory would look like this, right? But we have those things, but we can keep track of what they are, and you see the things agree with each other pretty well. Okay, so what that means is that it's not only is the thing is getting dense, but if you look at the average gamma as a function of time, you can get this from the theory, it very rapidly changes to some much smaller volume. It's going to as small as 0.4 here at the peak compression point, which means that the very nature of the quasi-particle in the middle of this compression is changing by a lot. The average nature of all the quasi-particles is changing by a lot, but the GHD theory is still working reliably through the time, which is to say, I think this is puts this generalized Gibbs ensemble equilibration approximation to the test to say it is clearly saying, doing the right thing over all this time in the experiment. Okay, so that's the energy. I'm going to go back to the distributions. I just have a few more things to show you. This is what I've already showed you. Experiment for the theory for the first 2 cycles. GHD working very well. By the time you get to the 6th cycle, now the shapes are starting to look a little bit more funky, but the experiment and the theory are still agreeing pretty much. The only difference is that there's a little bit of asymmetry on the experiment, and we can trace that to a very slight imperfect centering. Right, so basically the center of our distribution of atoms, if it's off by a little less than 100 nanometers out of the 17 microns, then it can give you the kind of asymmetry that you see over there. But to within the, and it's hard for us to keep it stable past that. But otherwise you see it's sort of, the theory is describing the experiment well, even though this is pretty far in, having had 6 cycles. This is a quantum many-body system. By the time you get to the 11th and 12th, this is the 11th, this is the 12th distribution. Clearly, although there are some similarities, the details aren't there. And I would say that we don't really know. This could still be experimental imperfections, or it could be that the approximations in GHD are starting to fail at this point. I mean, that's the whole point about trying to test a theory with experiment. At the point at which they don't agree, you don't know why it is. So, curious to see how that is. More experiments might tell, but it's worked pretty far. Now, if you look at something which is instead of the great detail of these distributions, if you just look at the energy as a function of time, this is a comparison of the energy in the experiment through the first 2 cycles, 6th cycle, 11th cycle, 12th cycle, compared to the calculation for the theory, and it matches well out to the 21st cycle. Right, so to some degree at least, GHD was doing a pretty good job that late. Okay, so in summary, we observed dynamical fermionization with strong coupling, and by doing that, apart from seeing the dynamical fermionization, it shows that we can measure rapidity distributions directly. So now we've done these very large track quenches. And in order to challenge these GHD approximations, which are the continuum limit and the local GG equilibration, and we find that they agree very well for pretty long times. So in the future, we can test GHD kind of descriptions with other potentials and other forms of integrability breaking. We can also purposely break these approximations, particularly the approximation of satisfying the GG on purpose, and then watch the approach to the local GG equilibration. So on a big picture view, there's integrable systems which GHD can describe, but it also works through non-nearly integrable systems. And then maybe there's a big gap between nearly integrable and generic systems. But since you can do such a good job possibly moving pretty far from integrable and using GHD as a description of many-body dynamics, maybe it's possible that that even though this is a big gap, that at least the GHD could be a sort of proto part of the description of quantum many dynamics in even more circumstances. Anyway, that's my talk. Thanks for your attention.
Thank you, Dave. That's good. All right, we have a couple of questions here, although we're short on time, so maybe I'll only ask two. The first one is Bill actually clarifying his previous question. So he said in a 3D BEC, the in situ momentum distribution is the Thomas Fermi in the Thomas Fermi limit is narrow, very Bose-like. After mean field expansion, as in Kasten-Dumm, the spatial distribution, which at long times is the momentum distribution, stays Thomas Fermi, which is to say that the momentum distribution got converted. But this has nothing to do with the atoms fermionizing.
Right. I'm just.
And then he adds, by the way, the GHD results are really cool.
Thank you, Bill. Yeah, what I'm saying is that the this expansion that we're seeing is this conversion from what is initially interaction energy. I mean, it's not just interaction energy, it's the initial wave functions, which then converts into a very dramatically different shape. I mean, I think it's true in 3D, it doesn't change that much. That was my point, is that in 1D, it actually changes quite a lot. You know, it's not, and, you know, furthermore, you know, we're doing these things without without parameters for fitting. You know, I mean, it quantitatively changes the way it's supposed to.
Right.
So, yeah, I guess I still, at some level, I'm not exactly sure what it is, although it does bring to mind a point that I think at least Bill would be interested in. And you can ask the last question, and I can. I just say this one thing, okay? That is this, when we showed this here, where we see the change in the nature of the quasi-particles as you go through here. I just want to point out that if you did this exact experiment with a real, honest to God, Tom Schroeder gas the whole time, for a Tom Schroeder gas, even though the momentum distribution changes in its shape entirely, there still would be no interaction energy, because there can't be any overlap of the particles over there, which means that the kinetic energy would be the total energy. So if you did this experiment with momentum for something which actually stayed a Tom Schroeder gas, it would just look like this. It wouldn't look like this at all. Right. So, you know, this, you know, some of these changes in the distribution are really, you know, these dramatic changes are not what you just normally expect. Like, it doesn't have to happen. You know, it happens only because of the nature of this change in quasi-particles. Okay.
Dan, in the tests of the GHD, is there a challenge to testing it numerically rather than experimentally? In other words, are the many-body calculations for the 1D systems able to extend as far as your experiments do, say the number of trap oscillations for the deep quench experiments?
I think not even close, right? That is, there is no way to make any significant headway through, you know, some part of this without the approximations of GHD, right? So, I mean, I'm no theorist. I know what the theorists tell me. I mean, it's just there is, in the same sense that we can't model the momentum distributions. I mean, the only place that you can do these exact modelings is in the limit of either very weak or very strong coupling, right? That's when you can do numerical theory and have it work out. Once you have to not use the crutch of infinite repulsion, then it's too much to keep track of all the correlations in the system.
Got it. Okay, and then maybe for our last question here, this is from John Simon. He asks, is there a reason to believe the GHD should break down after many cycles?
I guess I would say no. I wouldn't think that there would be reason that it would break down. The question is it still, are the approx? I mean, breaking down just seems a little bit too extreme for what I think it might do. It might be that you'd start to accumulate errors, which then you could see in an experiment.
But this is not like TDMRG where entanglement grows and you can't.
Right. It's not, because you don't have to worry about the entanglement growth. Part of it is that you have this this backstop of the distribution rapidities, which are locally conserved. Right. So, and that's the whole reason that it's possible to, it's a lot of coupled equations, but it's not, you don't have to keep track of a lot of entanglement. And it's sort of like the entanglement that's there in the system is within your cell. You have to satisfy this local thermalization thing, but otherwise, you're not, there's information that you're not keeping track of in the GHD, right? That is, it's not like you're getting everything from it. You're getting spatial distribution, you're getting rapidity distributions. If you tried to do anyway, it's not an issue because you can't actually keep track of the momentum distribution, but that would be a harder thing to do because that requires knowing all those correlations.
Got it. All right. So with that, Dave, would you mind unsharing your screen so I can quickly share next week's events? And while I'm doing this, I just wanted to remind everyone that I think in a moment in the chat, we'll have a link for the post-Vamos discussion with Dave. All right, so everyone should be able to see my slide now, hopefully. So our upcoming talks here, so there's the quantum science seminar next week, and this will be a young researchers talk. And so there are a number of different speakers, so I just thought I'd put up the topics. So there will be a talk on lattice gauge theories, on verification of quantum computers, and on polaron physics. And that'll be November 5th at 17 o'clock CET. And then next week in the Vamos seminar, we have Thomas Wienacht from Penn State University. And that'll, actually that's a typo, sorry. And his talk will be on coherent control of non-adiabatic dynamics in molecules. And with that, I think we will conclude. Thank you.